Good afternoon, everyone. It's my pleasure to welcome you at the very first Tuesday seminar of this year. And this semester, Mariusz Gromadzki and myself, Milan Ratajczak, will be leading the effort this year to organizing these seminars. And we are super happy to see so many people here in person. And we really hope that these seminars will be really held in person, less in a hybrid mode, because we think that interaction is something super important. For the scientists. So I'm happy to welcome our speaker that I will introduce in a moment, all the guests from other institutes, people from here, from the Warsaw Observatory, and also the master students, PhD students, and also the first and second year students that we are happy to have here. And our today's speaker is our new director of Observatory, Professor Tomek Bulik, who I guess doesn't need really a big introduction, but is working on the compact objects in the various areas. And today we'll be talking about the origin of merging compact object binaries. So Tomek, the floor is yours.
Thank you. So thank you very much. I'm so happy to see so many people here. It's been quite a while since this room has been so crowded. And I will be talking about the problem of the origin of merging compact object binaries. Merging compact object binaries have been detected with gravitational wave experiments over nearly last decade. And I'm so happy to say that time passes so quickly, and it's almost 10 years since the first detection in 2015. And since that time, the number of these objects has been steadily growing, as you see on this curve. So this is the effective four-dimensional space-time volume that was surveyed. And as a function of the volume, we see the number of detection, which is steadily growing. This graph shows the total number of about 100. But since that time, there is ongoing another observational campaign called O4, and the number has more than doubled. So now we have more than 200 detections, but I'm not really at liberty to discuss the details of those detections. Now, with these observations, we can measure several properties of these binaries. These are, well, the first and foremost is the chirp mass, which is a combination of masses that governs the shape of the signal in gravitational waves and is related to the change of frequency of the signal as the two compact objects inspire. Then we can measure the mass and mass ratio with poorer accuracy. However, we can measure the total mass for the most massive objects where we see the merger phase, so only the final phase of the merging process. Then we have two quantities related to the spin, which is effective spin and effective precession spin, and one of them is related to the amount of spin along the angular momentum direction, and another is the precession spin is related to the perpendicular, to the amount of spin perpendicular to the direction. And then we can have some statistical properties with 100 detections, or now more than 100. You can start thinking about distribution of parameters and not only be fascinated by individual objects. So these detections are shown here. So generally, there's a number of pictures like that. I chose this one. What we see here is the blue dots are likely black holes. The orange dots are likely neutron stars, and there are some blue-orange for which we are unsure. So there are two binary neutron star systems. So this is still a very low number, and I can say that in the next more than 100 detections, we haven't seen any of this type of systems yet. And then there is plenty of the binary black hole systems, and some there's some mixed systems here, and some for which we are not sure what, because these objects are a little bit too heavy to be neutron stars, and so they might be black holes, but our priors, our understanding of black hole mass distributions are such that we are not fully inclined to believe that. This is that the typical masses stretch from about 10 to about more like 60 solar masses, 60, 70 solar masses, and there is plenty in between. And that's in contrast to the binary black holes that are seen electromagnetic waves as accreting sources in X-ray binaries, which typically have masses of 5 to 10, maybe 15 solar masses. So what are the mass properties? If you look at the primary mass, you can fit some distributions to this primary mass. You can first fit something like a power law, like a single line. You can then try to see if there is any structure in this distribution, if there is any possibility to see that masses are grouped, and depending on this model, whatever you assume you fit, there is you get something different. But generally, what people see here is that this distribution of masses is not really like a flat. It's not featureless. There are some features like indication of aggregation of masses, or in terms of spectra, I could say that there are some spectral lines in the mass spectrum. So there is an aggregation around 15 to or so solar masses, then around 30 something solar masses. Then there is a long tail that extends all the way to 80 solar masses. And here it's like, single detections already. So that's very uncertain. But you see that the tail is stretching out quite far, and that this mass is, this is a log scale, this is linear scale. If you think that this is some type of a straight line, then this is an exponential power. Okay, so then we have the effective spin, and the effective spin is given by this formula. So if you have the angular momentum, and then you have two individual spins, then this is the mass-weighted average projected onto the direction of the angular momentum. So if this quantity can be between -1 and 1. If it's 1, then we have maximal spins that are oriented along the angular momentum. If it's 0, then we can have many situations that lead to 0. We can have spins in the orbital plane. We can have two spins that are in opposite directions and equal. And if it's negative, then there is some evidence for anti-alignment of the spins with the angular momentum. Then the effective precession spin is another quantity which is related to this composition of spins. Is the maximum of these two values. Q is the mass ratio. So essentially, it's either the larger value of this spin, or if this one is small, then there is this other value that is weighted by some combination of some function of the mass ratio in this binary. And this quantity is measured with much poorer precision than the previous quantity, the effective spin. Now, when you look at the measurements of this spin of this spin quantities, the effective spin is shown here. And what is interesting is that, first of all, if the spins were, this value of this effective spin is relatively small, it could be between -1 and 1, and it never reaches those maximal values. Second, so the width here is about plus minus 0.2. then the center is slightly to the positive values, which means that statistically, the spin values of the merging objects, merging black holes, is statistically they tend to be aligned with the angular orbital momentum. However, there are some objects for which this value is definitely negative. So there are some anti-aligned objects as well. And the second thing that you can see from here is that most likely the typical values of the spins are not maximal. These are not maximally rotating black holes for which spins are +1 or -1. Because then this value, the width would be much larger. And this, you can say, okay, but this maybe the spins are maximal, but they are in the orbital plane, which then would lead to much larger values of the precession spin, which is also centered on the value of about 0.2, with some large width. So from this, we can infer that most likely the spins of merging black holes are small, are not maximal. They're typically 0.2, typically 0.4, but it's not that all of them are maximally spinning. And now the statistical properties, given 100 detections for all of them, we have some estimates of their distance. Sorry for that.
Other detection.
That was my mother. So, whoops. Here we are. So we see that the rates increase with redshift. This is the quantity, the merger rate density, the number of mergers per unit volume per unit time. So this is the how often these things happen in a given volume. And you can model this based on the detections that we have and based on the selection effects that are modeled, and this value is increasing with redshift. And just to guide the eye, there's lots of quantities that evolve with redshift, and one of the quantities of interest is the star formation rate, which is shown here, which also increases up to the redshift of 2. Here we are not reaching the redshift of 2. And then it falls down, but we are not looking that far. We are only seeing up to about 1.5, so we are only seeing this part of the graph. And if you put the star formation rate in arbitrary units on top of that, it's just roughly, it is consistent. So it's not a proof, but it shows that these two quantities may be connected. So what are the challenges that this observational picture presents? First is the black hole mass challenge. And the black hole mass challenge is related to the fact that we see this high mass tail of masses. And we believe that black hole masses are limited to black hole masses formed in standard stellar evolution are limited by the winds and by the pair instability supernova mechanism. So winds depend on metallicity, and so the higher the metallicity, the more easily massive stars lose mass, and therefore by the time they are ready to form black holes, they simply don't have enough mass, and they cannot form too much massive black holes. And if the winds are small, and if the metallicity is small, and if they manage to have enough mass, then there is this mechanism of pair instability supernova, which is related to the fact that in this massive stars, temperature is so high that at some point you can start creating pairs out of photon pairs. And if you create pairs inside a star, you suddenly lose pressure, and the star becomes unstable. And in extreme cases, this can lead to the total disruption of a star. And theoretical calculations indicate that we shouldn't see, there shouldn't be black holes with the masses above about 65 solar masses. But this is a result of theoretical calculations, which should be verified somehow experimentally. So, but we see that there are these black holes, and there is no cutoff at 60 solar masses. The mass distribution extends to 80 something. So the ideas that come here is that maybe this mechanism doesn't work, or maybe that these black holes form in a different way, and they don't. Then they avoid this this limit, and so there may be hierarchical mergers. So you merge small black holes, add more black holes, and then there is no problem with the parent stability. Then there's the black hole spin challenge. Black hole spins, as I indicated in gravitational wave sources, are small, but black hole spins in accreting binaries, and some of them tend to be large. And there's a lot of papers about whether this is a significant discrepancy, whether this is a real problem, or whether this is these two things are consistent. First of all, I think that the black holes in accreting binaries follow very specific evolution paths, and these are not typical holes as those in gravitational wave sources. And then if you look at the spins here, these are the spins of black holes in accreting binaries. There seems to be a double peak distribution. So there are some with lower spins, and there is a group with higher spins. But I think that this is a challenge, this is a problem, and we have to think about it. And there is a recent paper saying that there is no challenge, but I think that the discussion is still going on. But one thing I can say is that I think that there are some arguments saying that typical spins of newly born black holes should not be very, very large. And one argument that I have is if you look at the spins of young neutron stars. Young neutron stars, so young radio pulsars, have spins and which we can measure about 0.1, 0.2 seconds. There are some spinning quicker, like the pulsar in the Crab Nebula, 33 milliseconds, but this is still, for a compact object, 33 milliseconds is a very slow rotation. It's very far from maximum. So we see that in formation, in core collapse, you can very easily form slowly rotating compact objects. Of course, forming black holes in collapses of massive stars is a slightly different process, but there are some similarities as well. And then I have another argument based on the fact that we observe long gamma ray bursts. Long gamma ray bursts are believed to be the objects that are formed when massive stars collapse, and at the collapse you form a quickly rotating black hole which forms jets that break through the star and then form relativistic outflows that we see as gamma ray bursts. And by observing the gamma ray bursts, we can estimate what is their rate density or rate in the universe. And we can compare it to the supernova rate. And the supernova rate is about 1 per second in the universe, while the GRB rate is much less than 1 per 100 to 1,000 seconds in the entire universe. So that means that forming these quickly spinning black holes inside collapsing stars is not that easy, because if it was easy, if it was a generic mechanism and all the black holes would be formed with high spins, then our GRB rate would be much larger, and that would be inconsistent. Okay, so then we have the problem of the separation. So we see this merging black holes, and we know that for a 30 and 30 solar mass black hole, in order to merge within the Hubble time, it has to start at the distance less than 30 solar radii, much less than 30 solar radii. And if we look at stars from which they should have originated, like the radius of a 30 solar mass sun on the main sequence, about 10 solar radii, and over the evolution, the course of evolution, the radii of those stars grow even larger. They can grow into 1,000 solar radii. So then there is a problem that once the system grows through the stellar evolution to make these black holes, in order to survive as two separate objects, they have to be far away, but then they have to be brought back to a very small distance, like 10, 20 solar radii, in order to be able to merge in the Hubble time so that we can observe them. So this is a challenge, and it has to be solved with the potential formation scenario. And then there are the merger rate densities, which I show here. So I just talk about the binary black holes. So if we talk about the binary black holes, the estimated merger rate density is about 17 to 45 per gigaparsec cube per year. And if you see a number like this, it doesn't tell you anything, it's just a number. The number has to be compared to something. So let me say what I can compare it to. So if we have a supernova in our galaxy every 100 years, and there is about one galaxy per 100 megaparsec cube, then the rate of supernova in the local universe in the same units is about 10 to the 5 per gigaparsec cube per year. Yes? So then if the rate of formation of black holes is roughly 10 times smaller. So black holes, stellar black holes, are formed at the rate of 10 to the 4 per gigaparsec cube per year. And if you compare this number, you see that about one black hole in 100 to 1,000 has to end up in a merging system. And it's, and this is out of all the black holes. So so some of the black holes are in the single systems. Some of the black holes are in very wide systems that are disrupted. Some of the black holes are in very systems that merge before as stars before they form a merging black hole. So actually, making this one merging black hole in 100 to 1,000 is not easy. I'm saying that this is quite a large number, and the mechanism to reform these systems has to be quite effective. And you can check that with the neutron stars, it's about 100 to 1,000 as well. So we have this challenges information, which is the black hole masses and spins, and I think that this can be overcome, especially the spins, as I mentioned. Black hole masses, we don't really know what is the minimum mass for the Pearl instability supernova. So, but the higher we go, the more we go into an uncertain region where we don't really know what is happening and why our calculations of stellar evolution are off. Then for the orbital separation to merge in Hubble time, we need to work a little. I'll show you the scenarios, and the scenarios can overcome that without too much trouble. Then the rate tells us that there is quite a lot of them, and we need a mechanism that is not very exceptional. You cannot invoke mechanisms that requires some very unusual conditions that happen very rarely in the universe. Okay, so what models do we have? The stellar models, and then we have primordial black holes. So for the stellar models, there's the binary evolution. So the binary evolution, isolated binary evolution in the field, like binaries in galaxies which do not interact with other binaries over the course of their lifetime. Then some of the binaries happen to be born in clusters, and there is quite a wide variety of clusters, from young open clusters, and most stars are born in young open clusters, where in the early days they can interact maybe with other stars or binaries. Then there are globular clusters, which formed earlier in the universe, and there is quite a number of globular clusters around the Milky Way, and in those clusters there is quite a lot of interactions between binaries. They can exchange partners. There is a lot of phenomenology. The nuclear clusters, which are massive clusters in centers of galaxies. And then there is the AGN disk model, where binaries form and are made to merge in AGN disks. So we have to have a disk around a massive black hole, and in those disks there is enough gas and, to make the black holes and come together and merge in time. Okay, so in all these stellar models, we have to say that the rate should somehow follow the star formation rate, which I'm showing again. So we expect that there would be a peak around the redshift of 2. If we talk about globular clusters, the peak globular cluster formation time was at the redshift of about 4. But anyway, maybe with next generation instruments, we might be able to see that. Then the other thing is that the stellar evolution strongly depends on metallicity. So when we talk about the formation, we not only have to take into account the star formation rate, but the star formation rate dependent on the metallicity, which was thoroughly investigated by a former student of ours, Martyna Kruśnińska, who made these beautiful maps based on observations that allow to see what was the metallicity distribution for higher redshifts. And then when we have, so this is the beginning, starting ingredient of those models. And then when we have the stellar type scenario, we have to start with star formation, go through the evolution to binary black hole formation. Then we have to let binary black hole mature and tighten the orbit, merge, and then gravitational waves travel towards us for some time, and here we are with the detection. So once we are in the detection, we have to go through all of these stages to simulate the process. Okay, so let's talk about the isolated binary evolution. This is a graph from an old paper with Chris Belczynski about the formation of massive black holes that was still done before the first detection. And the masses must come from stellar evolution, but there is the problem of pair instability maximum of about 60-70 solar masses. Then over the course of this evolution, there are some episodes of mass transfer. And these episodes of mass transfer also transfer angular momentum, which may lead, is likely to lead to if you transfer the angular momentum onto a black hole, that you will make the make spin align, or if they were anti-aligned in the first place. Rates, in a way, should follow star formation rate, but with some delays, because there is still a lot of time for the black hole in spiral. The typical in spiral times for the binary black holes in these scenarios are in the order of gigayears. Okay, and then we tighten the orbit through the common envelope mechanism, which is shown here. When after the formation of the first black hole, the other star is a giant, and there is an unstable mass transfer episode, which leads to ejection of the mass from that star, and this mass is ejected mostly at the expense of the orbital energy that of the system. So the system tightens, and if we tune it finally, then the system will not merge, but will form a tight binary here, and we can have a system that is initially tight enough as a binary black hole to merge in time. Then we have globular clusters, so dense stellar systems, 10 to 4, 10 to 7 solar masses. Here the point is that we have another degree of freedom. The binaries here, first of all, binaries with heavy components tend to sink towards the center, so the density of black holes and binaries containing black holes is much larger at the center of globular clusters, and there is a possibility for interactions and collisions between such systems, and in those collisions you can exchange partners and then make tight binaries of heavy objects. So there is a natural mechanism to form effectively binary black holes, and stars are not really bound to one partner in life. They can exchange partners and choose the one partner with which they can merge easier than in the traditional scenario.
And share screen again. Where am I? Oops. Okay.
Ten bar jeszcze zabierz z Google.
Anyway,
So
apologies
Yeah,
for this
seems that was some network problem.
problem, but here we are. So
I talked about the cluster evolution and listed the problems and advantages of this scenario. And let me now just show that with we can form something, calculate something like binary black hole formation efficiency parameter, which tells you how many black holes per each solar mass in a given scenario we form. And in the red it shows the cluster evolution, which really goes down with increasing metallicity. So it's the low metallicity field that can help. And for globular clusters, it's about a factor of 5 to 10 higher, and it goes down with metallicity much slower. The maximum value that you can obtain out of if you assume that the stellar mass function is the salpeter mass function, and then all of the black holes are making the merging black holes about 2 times 10 to minus 3. So this is above this line. That's where the absolute maximum for this value lies. So these scenarios, when you compare it to the maximum, they are about 1, 2 orders of magnitude below the maximum. So they are pretty efficient. The only point is that most of the mass in the universe is in the field, and globular clusters constitute about at most 5% of the total mass of galaxies. So, they can compensate for the small total mass with their efficiency, but they cannot really dominate. I think that these two scenarios are equally, or potentially equally contributing. So then there is the AGN disk models where black holes are born in stellar evolution, but binary black holes are formed in the disk, and there is some, this is aided by friction with the gas in the disk and this type of process with multi-body interactions, and mergers take part in the disk. And here, my main objection to this, so spins will be isotropic, and my main objection to this scenario is that the total amount of all the mass that is in AGN disks in all the galaxies is relatively small. It's about 10 to minus 4, 10 to minus 5 of all the stellar mass that ends up in disks. And therefore, even if you have the highest possible efficiency, you cannot really make up for this problem that this is such an unusual and exceptional environment that this scenario cannot make all the mergers that we see because of that. But some individual events, and like 1 in 100 or 1 can originate there. Then there are primordial binaries for which masses correspond to phase transitions, and but they can be below 1 solar mass, and if we saw something below 1 solar mass, that would be that, and we would know that we would have evidence that this is not a neutron star, but a black hole. Then this would point definitively towards the primordial mergers. Spins should be random and probably small, because these black holes originate in collapses of density perturbation in the early universe, it's very difficult to make those perturbations spin quickly, at least I think so. The rates do not have to follow the star formation, and they are very uncertain, but they also scale as f squared, where f is the fraction of black holes in dark matter, and I'll come to this in a moment. So let's compare it with observation as the time runs out. I talked about the basic rate arguments that the formation must be very generic. We cannot do the exceptional environments. So this dense star matter, dense star regions like globular clusters can contribute, but I'm skeptical about exotic models like the AGN list models, because they cannot really contribute unless you have a mechanism to gather a lot of black holes from other regions into those AGN disks. Binary evolution, masses, we see two heavy black holes. This is, I think, getting to be a problem, that making these black holes of 70, 80 solar masses is tougher and tougher. And you have to twist and turn and stretch your imagination to overcome the pair instability problem. Spins are slightly positive, and small spins I don't think are a problem, and the rates follow the star formation rate. So at least from these basic things, this looks well, apart from the masses. For the cluster evolution, masses can extend about the stability supernova. Spins should be centered on zero, and they are not. So spins are this effective spin distribution is not in agreement with this model. And in hierarchical mergers, the spin should be higher. So for higher masses, we should see a trend that effective spins grow when we, as a function of mass, and the statistic is still too small to decide that. The rates should increase with SFR, and maybe there should be a peak at the redshift of 2 or 3 or 4, where there is a peak of globular cluster formation. But that's beyond the reach of our detectors now. I have already criticized the model. There is one case, GW 190521, which sparked a lot of controversy because people found a flare in an AGN at the same location, and they were very excited about that. So maybe this is this 1 out of 100 that originates in the AGN disks, and I think the story remains to be solved. But anyway, the rates are very low. For the primordial, the distribution of masses can be very wide, but we don't see black holes below the stellar limit. So at least there is no need to invoke primordial. Then spins are positive, but they should be on the average 0. And why do the rates follow? The rate densities follow star formation rate? Then if they really follow, then this is some kind of conspiracy of the universe to confuse us, because there is no reason in this model that they should be following the same distribution. And there should be a peak of the distribution of merger rate at very high redshifts, which we cannot see. And there is this nice paper from this building, which I think shows that the fraction of black holes that form dark matter in our galactic halo in this interesting mass range is below 10 to minus 2, and that means that these rates are of the order of 10 to minus 4 per gigaparsec cube per year. So it is very difficult, in my opinion, to maintain the picture with many compact object merging compact object binaries originating in primordial black holes. with this OAUW observations. And then there is this other, there are the other constraints coming from X-ray and radio observations. So essentially, there are many arguments that make the fraction of dark matter in primordial black holes in this mass range really small. So these rates should scale and they are very low, and the spins are positive, so this is not expected. So to finish this, I have this nice, I think, chart, which shows the three models and how do they make with the masses, spins, and rates. So the binary evolution in the field explains the spins and rates, but has some problems with masses. I give it a yellow light because we don't really know what is the brainstem supernova limit and how that works. For clusters, masses are fine, rates are fine, but we have to have somehow spins that are slightly aligned with the angular orbital momentum. So I give it a yellow light here. And for the primordial, we see that it's similar to the cluster, but as far as the rates, I don't see a possibility to make the merger rate density from primordial black holes as large as we observe, as it is observed, given all the constraints on their density as a fraction of dark matter. And I'll stop with this. So I think that, okay, that we need more than one scenario, and I think we have a mix of binary and cluster evolution.
Thank you.
Thank you very much. Do we have any questions or comments? So maybe let me start. Do we have any constraints from the observations of gravitational waves? Do we have any constraints on the centricity of the binary systems?
The centricities of these binary systems should be very small, and we have not detected non-zero eccentricities yet. But in the globular cluster picture, we may have very short-lived mergers, so they form an unstable, maybe 3 or 4 object system, and then form a binary black hole, which merges on the order of 10 or so years. And those systems can have large eccentricities. And so we search for that, but we haven't seen it. But this will not be, your average type of mergers. Most of the mergers from globular clusters will either happen in the centers or will be ejected, and will have enough time to circulate. So that is something we look for, but we should. Yeah. So you're
okay. You can come if you want to.
Okay. So I have a question to you concerning cluster, yes, because the problem is with spin. So according to me, if I'm right, your assumption was that 2 black holes are almost not rotating, yes, just having small spins, and then in the globular cluster, say when they are merging, the output will be 0.7. But have you taken into account that you have, let's say, 3-body, 4-body interactions, and in this way you can have spins being, randomly
I was
located?
saying that for clusters, the average spin, the average effective spin, when you average it over many systems.
So taking also into account 3-body, 4-body.
Yes, because all these many-body interactions, you lose the memory of initial spins, of the relation between the initial angular momentum of the incoming 2 binaries and the spins. Even if they are aligned, then after 3 or 4-body interaction, the newly formed binary will have a random, essentially, direction of the spin, and there should not be alignment.
So In your final chart as a cluster, you have the nuclear cluster, globular cluster, open cluster, all type of clusters, or this is just globular?
Well, all of these clusters can contribute. I think that most of the work that we have done has concentrated on globular clusters and nuclear clusters. Now, open clusters can affect. I mean, I treat the open clusters as part of the field binary evolution, because most of the stars are found in open clusters, and then they dissolve, and then we see them as single binaries. But they may have had, these short episodes of living in a cluster initially.
This is not include the AGN disk.
Well, the AGN disk, I think, model is quite, depending, not very well defined and specified. So in AGN model disks, there is not clear to me where do the black holes form. I think that they can form most easily from stars that evolve close or within the disks. Then because of the dense gas, they can clump together. But the point is that the fraction of stars that live, fraction of all the stars that live in the disk or nearby the disk is very small.
Any more questions? Anyone on Zoom? Oops. I think there is something here. Oh. Oh no, okay. I think there was just that information about.
Okay.
Yeah. So I don't see any questions from Zoom, right? If there is any, please raise your hand or write, but I cannot see. Okay, so let's thank Tomek for the. And we meet here in a week's time, and there will be talk by Tomek Bulik, who'll be talking about some constraints of black holes from microlensing events, black holes masses. And just an information for master's students and PhD students, there's this notebook, like analog notebook, where you are asked to put your names. If there's any of you who haven't put it yet, hasn't put it yet, it should be somewhere there. Whoever has it, please. Where is the zeszyt? Yeah, it's there. So thank you very much.